In electrical engineering, power is very important. As we've discussed before, power is typically has two components that we work with. One is the reactive power and the real power. So the P we used to refer to real power, and then Q it refers to reactive power. Um, Average power is the portion of the power that is used to convert to non-electrical works like thermal energy, kinetic energy. So that's the part that actually does the work. So generally, if I've got a circuit or a device or a power generation or whatever, um, and I have like a let's say I'm a power generator, generating power for houses, then I would like, and if the house is represented as sorry, can't do a resistor, it's got to be an impedance because they have capacitors, the capacitors and inductors and everything and the instruments at home. So we're going to call this one Z load. It's always good to know what kind of a load allows us to deliver the maximum real power to this device. So our goal is to maximize P. So the best way to do that does, as we have discussed in earlier videos, any circuit, whether it's in phasor domain or time domain, can be turned into its Thevenin equivalent, which would be, in the case of a phasor domain of more RLC circuit, this would be a Z Thevenin, and then we would have a voltage here that is V Thevenin. It most likely is a variable, but for now let's just say V Thevenin. So our goal is to figure out what has to happen, what relationship has to exist for us to be able to deliver maximum power to our load. So our goal here is to deliver maximum power, and not just any power, real power. That's that P to load. Okay, a load, you can think about load as being the user, and let's say the rest of the circuit is the generator. So in a steady state environment, what we need to do is basically write the equation for this. So once we have the Thevenin equivalent, we basically do a KVL around the loop, and we can say, okay, I, that would be the I that goes this way. It's in phase, it would be V Thevenin divided by Z Thevenin plus Z load. Okay, now we got to get a little more specific here. A Z, whether let's say it's Z Thevenin, is going to have two components to it. It's going to have the real portion, which we typically refer to as the resistive side of it, and then it's going to have a imaginary portion. Might not have it. It could be zero, but as a general case, it would have a reactive, which we represent with X. So basically this, and then ZL, of course, would also has Thevenin. Like in your house, you could have a heater, but at the same time, you have a washing machine that has a magnetic coil on it and has capacitance and inductance and all of that on it. So so this is going to be this is going to be ZL, RL, and then JXL. So now if we want to find the real power, the easiest way to find it would be magnitude of I squared times RL. So if you want to try to find the magnitude of I squared, it would be basically the imaginary portion squared plus the real portion squared. So basically we're starting by plugging this back up here. We'll have V Thevenin here. We'll have R load plus R Thevenin plus J X load plus X Thevenin. Okay, so when we want to find I squared, it's basically going to be V Thevenin squared. that's I squared divided by R plus R, R Thevenin plus R load plus X Thevenin plus X load squared. Both of these are squared. Okay, so now we have the magnitude. We just simply multiply that by RL and it tells us what the real power is that we're delivering. Now, our goal is to maximize this. So when is it maximum? We know it's going to be maximum and minimum will happen when the derivative with respect to x of L is 0, because that's our variable. That's the only thing that we could vary. Partial derivative of x of L, and then we can do the same thing as partial derivative of power with respect to RL. So I'm not here, we're not going to go through the process to do this, but if you were to do this, you will find out that for that to be true x of x Thevenin has to be minus x load, or vice versa, and then you'll find R Thevenin has to be equal to R load. So the bottom line, what we have is said that in order for us to deliver maximum power to load, okay, we have to have ZRR. We have to have basically RL minus JXL equal to R Thevenin plus XJ X Thevenin. A shorthand. So this, if you look at this, the only difference between this and our earlier equation for ZL is the fact that it's got a minus sign right there. This is the definition of a conjugate. If you remember the word conjugate, let's say if you have a conjugate of AX plus B, I should write A plus JB, the conjugate of that is A minus JB. Okay, so that's how they write it. Okay, and then if you conjugate it again, it goes back. All it's doing, the difference between these two, to go back and forth, you replace J with minus J, and you can go between its conjugate and itself. Okay, so as a shorthand, we say maximum power, maximum real, I gotta be careful, real power is delivered to the load when Z load conjugate equal to Z Thevenin. Okay, sometimes they conjugate both sides. I can also, this is the same as if I write it this way, right? Or if you conjugate a conjugate, you get it back. So either one of these are fine. You may see it written in one of the two ways. So if I want the loads to get a maximum power, these have to be true.